Hello, today we're going to talk about IPv6. As you know, IPv4 has been around for quite so many years, but if you've also been using it for a while, you're also aware of its limitations, especially the fact that we're running out of address spaces, and we've been able to buy some time with the use of private IP addresses and subnetting, but eventually we're going to have to make the switch into IPv6. So the first thing you're going to notice about IPv6, it's 128 bits in length. An IPv4 address was 32 bits. It also uses a hexadecimal format, which is the numbers 0 through 9, the letters A through F. And instead of 4 octets, it's going to use 8 quartets. So it's going to be quite a bit longer, matter of fact, 4 times longer in size than an IPv4 address. So, moving on, we're going to take a look at an IPv6 address. And we're going to type this one out right here. Again, these are the individual quartets. And there's going to be 8 sections of them if you write out the address in its fully expanded form. We'll write this out here. And I'm not always the fastest typist, but we'll get this right. So if we look at it, count it, we see 1, 2, 3, 4, 5, 6, 7. So we need one more. So we'll just add something else in here. And again, notice each quartet is using valid hexadecimal characters. Alright, so that is our IPv6 address in its elongated form. There is a way to truncate this or make it smaller without changing the value of what it means. So we can write it out a little bit better. You'll notice on this IPv6 address that we have some quartets that have all zeros. We have some that have leading zeros. And the leading zero right there is 0021. If you think about it, 0021 is the same thing as 21. So why write 0021 when we can write just plain old 21? Get rid of those zeros. We won't need to write them. And then instead of doing 4 zeros, we can do a single zero. Now, however, because of the fact that these zeros are all in quartets that are contiguous or side by side, I can even make this further by referencing : as opposed to having 0:0. And then the : will represent a range of contiguous quartets of all 0. So instead of doing those 2 quartets, we're going to do a : So we're going to rewrite this address now in its truncated form. So we'll type 2001. Can't bring this one down any smaller. We're going to go from 0021 to 21. And now we can go : 25C, which was already truncated, 688A, and 23B1. So you can see it is written down a little bit lower than having to write that whole thing out there. If you count the quartets, again, you'll notice that there are 1, 2, 3, 4, 5, 6, and what's missing are 2 with 2 sets of zeros. Now, look at this address right here. If I put in 2001 : 3321 : ABCD, the problem here is I see 3 quartets. We know there has to be 8. So there's 5 missing. Is it 4 sets in the first quartet of : and then 1 in the second? Is it 3 here and then 2 here? Is it 2 here and then 3? Is it 1 there and then 4? We have no way of knowing. So we cannot do the : twice in abbreviated form of an IPv6 address because we just have no way of knowing where those zeros would be. So we would have to use : 0 as opposed to the : in that example. Now we're going to go ahead and take a look at how to expand an address that is valid. So we're going to write out a compressed format of an address. All right, count your quartets that you see visible. 1, 2, 3, 4, 5. So that's telling you that you need to add 3 more because you need 8. Those 3 more are going to be all zeros. So we'll underline the 5 we have. 3, that 0 is 1 right there. And we can see that we're missing 3, and those 3 of all zeros are going to substitute in where that colon is. You'll also notice, and we'll get to it here in a second, let me move this so you can see it a little bit better. So we're going to go replace the colon with zeros, 3 quartets. Now the 33 can be expanded to 0033. It means the same thing. And then 14, A0. The single 0 could be 4 zeros, and then the last one would be 2296. And that's how you would bring back a truncated one to its full size. All right, moving on, we're going to talk about the types of IPv addresses that we have. And first we're going to take a look at IPv4. So in an IPv4 types of network addresses, we had unicast, which is a one-to-one transmission. We had multicast, which is a one-to-many transmission. And we have broadcast, which was one-to-all within the subnet you were in. That's IPv4. Let's see how it changes or stays the same in IPv6. In IPv6, we're still going to have a unicast, which is still one-to-one. We can still use multicast, which is one-to-many. But we no longer have a broadcast. Instead, we have something new called an anycast. An anycast is quite different. It actually really helps with performance issues and speeds things up for the clients. So to demonstrate this, I'm going to use some images here. And let's suppose that you have 2 servers, DNS servers, on your network. So we're going to bring in the icon for, or an image of a server. And then I'm going to duplicate this image. So I have 2 servers showing here. Now, in this anycast, if you did not have an anycast, and you had clients assigned to use a certain DNS server, let's say you had 100 hosts going to DNS server 1 and only 20 going to DNS server 2. So you're essentially going to overload one server while the other server is underutilized. So instead what you can do is you can assign a special anycast address in addition to your normal address to the server. In this case, the anycast address is going to be the same on both servers. Okay, so we'll demonstrate that here. So we're going to go ahead and add that in. So we're going to say the IPv6 address is set to this as the anycast. Okay, I'm going to copy this out. Oh, didn't mean to do that. Let's put it back. I'm going to copy this, paste it, and notice that these 2 servers are both going to have the same anycast address. Now, in this case, the anycast address are the same, so if you're a client and you say go to this IPv6 address, it's going to go to the nearest one that can service it quicker. And it makes it a lot easier when you have a lot of clients so that you're not directing them to just one specific device, but instead go to the device that makes it a lot easier. So we now have multicast, unicast, same as before, but anycast is new to IPv6. It makes things performance-wise a little bit better for us to use. All right, moving on to the next new piece of changes in IPv6. Let's get a new whiteboard open here. In IPv4, we had private IP addresses, we had public IP addresses, and we had some special IP addresses, specifically the loopback adapter, which represents your single device, and a special type of address called an APIPA, automatic private IP address. In IPv6, we're still going to have a private, but it's now called a unique local address. Often you will see this abbreviated with ULA. We're going to have the public address, which is now called a unique global address, or global unicast address. And we are still going to have a loopback, but instead of APIPA, we're going to have something a little different called a link local address. And we'll explain these out here. So let's compare the two together. The private address in IPv4, 10, 172.16 and 172.31, or 192.168, depending on where you were pulling it out of which class, is going to map in its features, at least from how it's used, to that unique local address over here on the IPv6 side. And instead of it being a 10, 192, and so forth, it's going to have its own special beginning quartet as well. I'm going to see this right here. And actually, I just typed that incorrectly. So let's get my eraser tool. Take that off. Say it's actually going to be FC, doing it again, 0, 0, and then you're going to see colon, colon, the remainder, and then /7 for the first 7 bits. And that will identify this as a unique local address. We can still route it within our network, within our enterprise, but it won't go on the internet. What will go on the internet is the public address. The public address is going to map to the unique global unicast. And the way the INA has this set up right now is any address starting with 2001 can be assigned now to these ISPs around the world, and they can start leasing these addresses out. And so eventually 2000s will be used, and 3000s, and so on and so on. It's going to take years and years, if not in our lifetime, before we're going to see any possible, total elimination of these addresses. The loopback address in IPv4 was 127.0.0 to 1. Remember, that represents the device you're on. So for example, if you ping it, you're pinging yourself. And we have the new one now is : 1, which would be elongated out to 7 quartets of 0, and then the last one of : 0001. Now, this link local is totally different. So to understand this, we need to understand how the APIPA was actually used in IPv4. In IPv4, when you set up a DHCP server and your client, your host says, I need an IP address, it goes to the DHCP server. If it talks, it gets one. But sometimes, for whatever reason, you can't contact DHCP. So it's going to try, and eventually it's going to say, I give up. When it gives up, it's going to self-assign an address of 169.254, and then the last 2 octets will be self-assigned by the host, and come up with this uniquely private IPv6 address, APIPA address, that was specific to a /16 network. Trouble was, that address, you couldn't talk to devices that were statically assigned with a /24. So instead of waiting till there's a problem in IPv6, they created a link local address. This one is going to start with FE80, and it's going to automatically assign itself an IPv6 link local the minute you turn IPv6 on. and the local host will assign the remaining portion of that. And so an FE80 will always be there, and it will represent an IPv6 link local address. And we'll take a look at this in just a second. Okay, so we're going to take a look at this on an existing system. And I like to use the PowerShell as opposed to the command prompt because I think it's much more versatile and it would be a good thing for you to start getting used to. You can still run your regular commands in here like ipconfig, and they work just fine. All right, so take notice here of my Ethernet adapter. Notice that I do have an IPv6 link local address, but I don't even have a unicast local address because I'm not using IPv6, but I have it enabled. Now, you'll see the address here, but at the very end, you see a %21. We will come back to that and discuss what that %21 means. It is not part of the actual IPv6 address. So, next thing we're going to do is let's take a look at this using some PowerShell commandlets. PowerShell commands are called commandlets. They have a verb dash noun. So when you run a command, like get is the verb, and then net or whatever you're going to write is the noun. So I'm going to use get net adapter to see my network adapters on my system. The column right here, the if index, if stands for interface. Notice that the Ethernet adapter is on interface 21. That tells me, if I go back to that IP config again, at the very end of that link local, what did you see? You see %21. So when this address goes out, it knows which Ethernet adapter this link local address is assigned to. Because you can see the one below it under VirtualBox, that's using a link local as well, but it's assigned to that adapter. So the GetNet adapter is a way for you to actually see that. To see your IPv6 address, you use GetNet IP address. Best thing to do though is to pipe it into a table format so it's a lot easier to see. So there are my interface indexes, my addresses. You can see the prefix length, which is telling you essentially how many bits are in the network for those IPv6. And then you can see some IPv4 addresses, the loopback and so forth, also located on there. And you can see the interface index is 1 automatically for a loopback adapter. What's really cool about PowerShell is I can customize this output. I don't need to see, for example, suffix origin, prefix origin. So I can actually request PowerShell just to show me what I do want to see. So we could take a look at that. So what we're going to do here is we're going to run the command get net IP address again. Oh, sorry. Before we do that, I want to talk to you about the MAC address. The MAC address, we're going to look at that because that's going to be important for the next thing that we're going to see. But I want to see just certain pieces of information. So GetNet adapter, I'm going to go to Format Table, output it to that, and then I only want to see the properties of the interface description and the MAC address. So I can just extract that. And now I got a much more simplified view of what I'm looking at. What we're going to do now is we're going to assign or talk about how the host portion of an IPv6 address can get assigned. If you've ever configured a DHCP server, an IPv4, you had to put in the scope, the range of addresses that can be assigned. In IPv6, though, that would be a lot to assign. There's a lot of values, a lot of range. So instead of doing that, what we're going to do is we're going to let the DHCP server configure it using our local MAC address. See how this is going to work. If we look at this IPv6 address from before, we break it into two pieces. The first part represents the network part, and the second part represents the interface ID, which is the part that is unique on that network. So instead of having to come up with a range of addresses like you see there, we're going to use the MAC address. But look, this is a 128-bit address, so that means the network portion is 64 bits. The interface portion is 64 bits. How many bits are in a MAC address? Only 48. So it's not going to fit. Well, it will fit if we stuff it. If we do some padding of some additional information in here. And I'm going to show you how that's done. So we're going to create a new whiteboard. So keep this simplified. We're going to put in the network portion of an IPv6 address here. Okay, so we're going to say that that is our network portion. And now we want to use the MAC address to backfill in the interface. So to make this easier, I'm going to go ahead and copy and paste our list of MAC addresses here so you can see what we're going to do. Now grab that and bring it into our whiteboard. Make this bigger. All right. So we're going to take that Ethernet, that Realtek, and we're going to use that MAC address of 1062E51473EA, but we're going to pad it so that it fits to all 64 bits. So we're going to start here by going colon 1062 in the next quartet, colon E5, and we're going to stop. We're going to pad here the next two bits, FF, and then FE to start the next, and now we'll complete out the rest of the MAC address. So 14, and then the last quartet will be 73EA. Let's expand that out. So let's map this up. So we've got our MAC address buried in here, and I know it because of the FFFE right in the middle. So this is called an EUI 64 format. And you'll see this on certification exams. And it stands for Extended Unique Identifier. Because what you're doing is you're extending the MAC address to come up with the unique portion of the interface address. So let's take a look. So we're going to highlight the relevant portion. So on here, 1062E5 goes to that portion. The FFFE is stuffed in the middle right there. And now we're going to go ahead and see the last portion. We'll change the color and make it easier to see. So 1473EA, and if you look down at our MAC address, 1473EA. So we can let the system create its own unique local identifier, because MAC addresses are unique, by stuffing it with FFFE in the middle so that we can extend this out to the 64 bits. And that's our first start on IPv6 learning tonight. Hope you enjoyed it.